Executive Vice President here at InCab America, and this is OPGW Engineering 101. We're going to be discussing some of the basics of OPGW cable design. In fact, I'll cover more about that in a moment. So let's just keep going. So we are RCEP compliant, which means that we can give continuing education credits if you would like them. At the end of the presentation, I'll talk about how you can get those if you want them. And hopefully the presentation is worthwhile whether you want them or not. So the purpose statement, as I say, this is about OPGW engineering, and that is perhaps better broken down on this slide. So the goals after this class is I want you to understand the basic types of OPGW that are used today and understand the advantages and disadvantages of each type. What are today's best practices in the design and manufacturing of each type? Understand what drives OPGW cable design. I especially want you to understand how to calculate fault current capacity, how you should determine what your fault current capacity rating should be, and then how you should be able to assess whether a given cable design meets your requirement or not. And then we'll talk about lightning performance. We'll close out with that. So we have some ground rules, and today is a little bit unusual. I don't know what it's like where you are, but I'm in Texas, near Arlington, Texas specifically. And it's cold here today. Right now it's 23, which is cold for me. I'm a Southern boy, born and bred in the South. So when it gets below freezing, that's bad for me. So that's about -5 Celsius. So it's cold here. And we had a snow/ice storm last night. Again, relative for Texas, it's probably, if I'm looking outside, a quarter of an inch or something, but you know, that makes chaos here in Texas. So I am concerned about the stability of my internet connection. If it drops off, trust me, I'll be back. I have a backup plan if that happens, but it'll be outside my control. I'll just have to react. So anyway, we've already done the introduction and sound check. Presentation itself would be about 50 minutes. We'll have a question and answer at the end, which we'll be able to do via chat. We might also make it possible, if we can do it, for people to just vocalize their questions. We'll see how that goes. The questions should be related to technical issues only, you know, on the scope of OPGW cable specifically. You know, we don't want to talk about business here. So like if you've got an order or want to place an order with the InCab, we love that. But now's not the time to talk about stuff like that. So let's go ahead and get started. So first of all, optical ground wire, the governing standard. I need to update this. The IEEE standard is 1138. The 2009 edition was still in effect, but last year a revision for 2021 officially released. So this needs to be updated to 2021 is the new edition. There weren't any big changes from the 2009 edition, but there were some. And for our international guest, I should also mention that there is an IEC standard for optical ground wire 60794-something that's used commonly outside of the United States. So some countries go by the IEEE, other countries go by the IEC. The two standards are fairly similar. Again, there are some differences, even some that I could characterize as significant, but they're pretty similar. And as a reminder, the function of OPGW is it replaces a traditional shield wire or a ground wire. When you say shield wire, you're emphasizing the lightning protection aspect of a shield wire, or of the cable, I should say. If you say a ground wire, you're emphasizing the fault current capacity, but the two terms are used interchangeably and they're referring to the same cable. So an OPGW, since it's replacing a traditional shield wire or ground wire, it's providing that protection from lightning, and it's providing that path for fault current. And to those two functions, we add optical fiber for data and communications purposes. To orient everybody, we need to go back a moment and talk about fiber itself and loose tubes. And I'll explain more about why loose tubes are important. And the reason that we're going to talk about these is that these set the stage for understanding the performance characteristics and specifically the performance trade-offs of the different OPGW designs that are used today. Fiber and loose tubes, the basic concept apply whether you're talking about OPGW or all dielectric self-supporting cable, ADSS. So fiber, to begin with, for OPGW, low water peak single mode fiber is overwhelmingly the most commonly used type, like more than 90% of the fiber. We here at NCAB and before, I had worked at Brood Cables for 20 years, and before that, another fiber optic cable manufacturer. So just a brief side about myself. I've been working with optical ground wire and fiber optic cables for nearly 30 years now. And before that, I did work with conductor too. So I've been working with aero cables for more than 30 years. In any case, back to the subject. So in my career, well over 90% of the fiber that I've used has been low water peak single mode fiber. The governing standard for that is this ITU-T G652. That's an international standard. Everybody uses this standard for their fiber. An example of this type of fiber is the Corning SMF28 family of fiber. So they began with Corning SMF28, and then it was 28E, and then 28E plus, and then 28E plus LL for low loss. And the current version is Corning SMF-28 Ultra. And we at NCAB process quite a lot of that. An important takeaway is from low water peak single mode fibers, or just plain vanilla single mode fibers, is that they're splice compatible with one another. So you can take Corning's product and you can splice it to OFS and they'll work fine. Corning and OFS will each have their reasons why they think their fiber is slightly better than the other guys. But the point for you as the user is that they are splice compatible. If you've already used Corning, it's okay to get some cable with OFS fiber in it and splice them together. They'll work fine. In general, you can go about 60 to 90 miles without repeating or regeneration. The next most common type, but again, it's a quantum drop down that what we see is so-called non-zero dispersion shifted fiber. It has its own ITU-T standard. The best examples of these are Leaf and TrueWave. These are not as readily splice compatible. You can do it, but you can also cause problems when you do it. And it's kind of beyond the scope of today to talk about why that is. But the reason that people use this fiber is to either get longer distance or to boost bandwidth by being able to use dense wavelength division multiplexing, DWDM. Again, the most common, overwhelmingly by far, is low water peak single mode fiber. The most important fiber performance specification is attenuation, and attenuation is simply the loss of power over distance. It's generally or most commonly expressed as dB, so decibels per some unit length, most commonly kilometers, but you could do dB per mile, you could do dB per 1,000 feet, you could do dB per furlong if you wanted to. But it's loss of power over distance. So decibels per whatever unit of distance, with kilometers being by far the most common. And what this means is if you inject 10 dB of power at the start of your link, at the end maybe you get 9 dB of power. You've lost some power over that distance. Another important performance specification is chromatic dispersion, and that's the tendency of the signal to spread out over distance, but we're not going to talk about that today. We do have a separate webinar called Fiber 101, where we talk in more detail about attenuation and chromatic dispersion. For today, this is it. So it is important, though, when you're specifying your OPGW to at least have a specification for that attenuation value, because that value really is critical for the performance of your cable, optically speaking. And we would say that it should be specified as the maximum individual after cabling loss. And so what this means, maximum obviously is maximum. So the loss should not be greater than what you specify. The individual means each and every fiber, and after cabling means after the fiber has been put into a cable. The reason this last one is important is that the cabling process involves handling the fiber multiple times, right? You buy the fiber, first of all, you have to get it colored, then you have to put it in a tube of some sort, then you have to take that tube and put it into a cable. Those are your minimum processing. So you've touched it at least 3 times as the cable manufacturer, and each of those times can increase the attenuation or the inherent loss of power in that fiber by just a little bit. If you do a good job during your processes, you keep that to a minimum, but if you do a bad job, you can have a lot of it. So if you as the user base your specification on just the bare fiber limits as it's delivered from the fiber manufacturer, you know, the cable or can do a poor job and you can end up with high attenuation, and yet they can say, well, you know, sorry, but you didn't have a limit for the final cable, you just had a bare fiber limit, and when we bought it, it was fine. So you really do yourself a favor by applying your limit to the finished cable. I think each and every fiber, you're probably saying, gee, what else would it be? Well, there are some companies that try to get you to take an average across a reel. And the obvious problem with that is that you could have one fiber with very high attenuation, maybe even to the point that that fiber is not useful to you. But the average for, say, a typical cable is 48 fibers. The average could still meet specification. So um, all the good cable companies could easily agree. Some may grumble a little bit, but they should still be able to agree that that limit that you specify is going to apply to each and every fiber. You do not have to accept averaging. Bidirectional averages, that means that the fiber was tested before it left the factory on both the inside end of the cable and the outside end of the cable. My position on bidirectional averaging is starting to soften. For some of you that have heard me talk before, you may be shocked about that. But yeah, I'm starting to soften on that. The reason is that as fiber counts have gone up, it's taking more time to test. And the fiber quality these days, and with today's production equipment in the cabling processes, is such that you really don't see much difference, like hardly any at all, between the inside end and the outside end. I still think it's the better practice because as a cable supplier, I want to make sure that nothing happens to fibers during my production processes. And the ultimate concern is that a fiber has broken. And bidirectional testing, you catch that 100%. One directional, which is typically just shooting from the outside, um, you can miss it if you're not careful. You have to have good processes in place to make sure that that's caught. But it's kind of becoming a practical reality, and a lot of cable companies are going away from bidirectional averaging. We'll see where that goes. So my position is softened. I've not changed it. I've just softened it based upon new information about what's going on in the market. As I mentioned before, attenuation is expressed in dB per kilometers most commonly, and at these specific wavelengths, 1310, 1550, and 1625 are the most common. There are others, but really you've got it covered if you do these three, and really of these three, the most important is 1550. If you have a fiber that's bad at 1550, it's likely also bad at 1310. And almost assuredly bad at 1625. But it tends to be, fiber gets more sensitive to bending as the wavelength increases, so the reverse is not true. You could have a fiber that tests good at 1310, but is bad at 1550. But the reverse is not true. If it tests bad at 1550, or I'm sorry, if it tests good at 1550, it's not going to test bad at 1310. This is also the most commonly used wavelength, so it gets you a good benchmark. So if you only wanted to worry about one, especially for your incoming inspection, right? When you get the cable, you should be doing an incoming inspection. And if you wanted to reduce testing time, you could say, well, let's just test at 1550. I would say that's a pretty good process there. You're going to catch 99.99% of problems if you were doing that. What limits should you specify? Well, for your standard single mode fiber, 0.34 at 1310, 0.20 at 1550, and 0.22 at 1625 are good, very good limits today. Good cable companies can meet these. I still see customers using limits of 0.4 and 0.3 and not even specifying at 1625. You can tighten your spec. Good cable companies can meet these. And if the non-zero dispersion shifted fiber comes up, well, good limits for that are 0.22 and 0.24. There are other fiber types that do come into play, but for today, I'm just going to say if you've got some, you probably have a specific need, maybe a customer who wants you to use multi-mode fiber to support them, or some very special application. So basically, this is in the category of give us a call. But the two types of multi-mode fiber that are commonly used are 62.5 micron in the United States and 50 micron, mostly outside of the United States. But I'm seeing a lot more 50 micron in the United States when we see it, not with OPGW, but with other types of cable. And 50 micron is often used for sensing applications. There is a growing interest in G654 fiber, and the concept is that it's trying to give you the versatility of standard single mode fiber, but with the added distance and bandwidth of a non-zero dispersion shifted fiber. Corning has a product, it's Corning TRX fiber is what they call it. So there, we'll see what happens over the next few years if that's going to replace it, replace traditional standard single mode fiber. So we talked about fibers. Now I want to talk about loose tubes, because for aerial cables, OPGW and ADSS specifically, loose tubes have out. There is still something called tight buffer, or sometimes called tight structure. You do see that tight tight concept applied to indoor cables and sometimes even to duct cables going underground. But for area cables, loose tube construction won the design war like 20 years ago. Everybody offers loose tubes for their aerial cables. A few also will offer tight, but some will only, and InCab is one of them, only do the loose tubes for aerial cables because that's the best design. In the loose tube design concept, you lay the fibers in a sinusoidal shape inside the tube. What that allows to happen is when the tube is elongating, which it will do in an aerial cable under loading conditions, so wind or ice, will put a load on the cable and that will cause the cable to stretch. And when that's happening, the tube itself is stretching and the fibers initially don't see the force that's causing that stretching. Rather, they just start to flatten out. So at the beginning, you have a length of fibers that's slightly more than the length of the tube itself. Typically, it's around 2.5%. Could be more. 0.3% is even better. It shouldn't be less, in my estimation. And then when it's beginning to stretch, the tube and the fibers are flattening out, eventually get to a point where this ratio goes to 1. So the fibers are straight and they're stretching. So they're experiencing some of the force that's on this tube. That point is the zero fiber strain margin. That's typically expressed for the cable in percent rated breaking strength of the cable. This excess length over here is called excess fiber length. And that's a very important parameter for really any cable, but especially any aerial cable. And as a general rule, higher is better. There are some exceptions, extreme cold weather, but we're talking minus 40 and below. Too much of a good thing, too much EFL can be a problem. But in general, higher is better. You can understand that if I put too many fibers in a tube, I can't get this shape. But there is a limit beyond which I essentially force the fibers to flatten, and that'll come back. And when the fibers are straight, that means they begin to experience the strain sooner, which effectively is to say that the EFL is lower, and so is the zero fiber strain margin. So these work together. Another concept for and then another way to increase EFL or zero fiber strain margin is to take that tube and strand it. When you strand a tube, like you see in this figure here, you're also increasing the EFL because of the extra length it takes to make this helical shape that you'll get in the tube when you strand it around something. And you can easily get somewhat in the neighborhood of 2.5%, so a factor of 10 more than what you can get in the tube itself just by stranding the tube. And then the last concept is what do you do if you have more than 12 fibers? Because 12 fibers, there are 12 standard fiber colors, but as fiber counts and cables have gone up, the requirement to put more fibers in a tube has gone up, more than just 12. And for practical reasons, there are two technologies that have been developed to deal with that. One is bundling, where you'll take a group of 12 fibers and wrap them with a color-coded thread. That's often called a bundling thread or sometimes a binder thread. That's one technique. And splice techs often like that because it makes it very fast to separate the one bundle from another, one group of 12 fibers from another group of 12 fibers. The trade-off, though, is that can reduce freedom of movement. That's a livable trade-off. With today's production equipment, you should be able to get a nice consistent shape like you see here. And so the whole bundle, if it's wrapped, should still move well as a group. technology was different about 30 years ago, didn't work as well, but today it works well. The other technology that's used is ring or band marking. That's where you take the 12 fibers, 12 fiber colors, you repeat those colors, but you add a little black mark on it, on the fiber. And that works too. And keep that concept in mind. That allows fibers to have individual movement, but it does mean you have to find the blue fiber, and then you have to find the blue fiber with the black stripe, and then you find the orange fiber and the orange fiber with the black stripe. And so that it makes it a lot slower to separate the fibers into their groups. But remember that for later. So we've talked about fiber and we've talked about loose tubes. Now we're going to take those tubes with fibers in them and put it into a cable. Over the decades, there have been other types of OPGW designs than the ones I'm going to talk about today. But today, there are basically three types that are used. We have center tube designs, which has two flavors. A plain stainless steel tube in the center of the cable surrounded by wires, which could be aluminum clad steel or aluminum alloy, depending upon the electrical or mechanical properties that the cable designer is trying to achieve. Or you can take a stainless steel tube and surround it with aluminum. This could be by inserting it into an aluminum pipe, or it could be by cladding it with aluminum. But the concept is that it's still a center stainless steel tube with aluminum around it. And around that, you again put wires. Again, aluminum clad steel or aluminum alloy, depending upon the exact electrical and mechanical properties that you're trying to achieve. So these are both center tube designs. Next is aluminum pipe type design. In an aluminum pipe type design, you have a nice aluminum pipe. And inside that, you use plastic buffer tubes that may or may not be stranded around a center element, depending upon the cable manufacturer. And last but not least, there's a stranded design where you take a stainless steel loose tube and you strand it around a center element with some wires. You might have one tube or three tubes or two tubes or as many as six tubes is what I've seen. But you strand those tubes around something. And you'll recall that when you strand a tube, you get a higher EFL, which in turn means you get higher zero fiber strain margin. And then around what you've stranded here in the center, you put an outer, at least one layer of outer wires. Again, aluminum clad steel or aluminum alloy wires are used depending upon the exact electrical and mechanical properties you are trying to achieve. Okay, so now we'll talk about each, the advantages and disadvantages of each specifically, and then what's the best practice for each. So first up is the center tube design. An advantage for all of these is that they are loose tube construction, but we're going to learn that loose tube construction, there's loose tube construction, and then there's loose tube construction. We'll see that the zero fiber strain margin will vary across these design types. And that has a lot to do with whether the tube is stranded or the geometry of that stranding process. We'll see that in a moment. But they are all loose tube, again, in contrast to the tight construction. Stainless steel tube in the center tube design provides superior protection for the fibers. I will tell you that I have a bias. This comes from the fact that I worked with conductors before I began working with OPGW, and I like metal cables, which means I inherently like stainless tubes as opposed to plastic tubes. And I like OPGW in contrast to ADSS. Not that I think ADSS is bad. It's just if you ask me which I like better, I like the OPGW because it's a metallic cable, because I worked with conductors before. I like metals. So anyway, I like this stainless steel tube. I think intuitively it should be obvious to the casual observer that stainless steel tube is going to provide better protection for your fibers long term than plastic. These designs are very mechanically and electrically efficient. They give you very small diameters, and that is a significant advantage. And because they are so efficient in their design construction, they tend to be very cost effective. So in the real world, that's an important advantage. But they do come with some trade-offs. Of the three types, these designs have the lowest zero fiber strain margin. About the best you can get is 40 to 50% of the rated breaking strength. So keep in mind that the NESC Rule 250B limits allow, under fully loaded conditions, 60% rated breaking strength. Your everyday tension is going to be a lot lower, probably around 15% rated breaking strength, but 15, maybe 20, somewhere in that neighborhood. What that means with these design types is that under everyday conditions, the fiber is not experiencing strain, but under the fully loaded condition, once you pass whatever that zero fiber strain margin is, the fibers are experiencing some strain. Now, fiber is quite strong, 100 kpsi specifically, so it's quite strong, but it is glass, and that makes it brittle. And I think you can understand that you do get a non-zero risk, especially with cyclic loading, right? Today in Texas, center tube designs are probably experiencing strain. Tomorrow, maybe not, but then a day after that, you could get strain again. So that kind of cyclic loading over time, there is a risk of damaging the optical fibers. Initially, attenuation will go up, but it can progress up to and including fiber outright breaking. So you'd like to avoid that, but there are times when taking that risk is a appropriate solution. Another disadvantage is, even though I've told you how much I love and adore stainless steel loose tubes, splice techs often hate them. They perceive it to be more difficult to splice. I counter that, well, it's not difficult, it's just different. But you'll understand that techs who work with fiber optic cables more often are working with ADSS or duct cable on a day-to-day basis, and those cables use plastic tubes. So they're very familiar with working with plastic tubes. They often have less familiarity with working with stainless steel, and so they initially approach that with some trepidation, shall we say. But if they're shown proper techniques, they won't have any difficulty doing it, but you still have to overcome that perception. These cables tend to have less flexibility, and they're more susceptible to being deformed or crushed, which is important when you're doing stringing. So that can cause you problems. Because of the lower flexibility and higher susceptibility to being crushed, it means they often require an anti-rotation device during stringing, which is a hassle. It also may mean that the stringing blocks have to be larger and that there are other pulling restrictions, which effectively limit how far you can pull. And so that can mean more splice points, and more splice points means more money. You're also limiting your fiber count. Some suppliers can only do up to 48. The most that I'm aware of, and the most that NCAP can do, is 96. So when you make this design, how do you make the best version of it? Well, I'll start off at the bottom. You want the fit of your wires to be conservative, and when you're stranding, you want to use a conservative lay length and a good preforming, which is a like a shape that you put into the wire before they're actually stranded around the tube. You want all of those parameters to be very conservative, you as the user. Now, manufacturers especially like long lay lengths, because then one revolution of your machine means more productivity and profits soar, right? But you as the user should be concerned about this, because that actually reduces cable performance. And when it comes to the stranded designs, it can actually lower your EFL and your zero fiber strain margin. So you have to be aware about that. Don't take things like this for granted. When you're making the tubes, you've only got that sinusoidal shape that you can get in the center. So you got to make the most of it. And what a cable manufacturer should do is juice it up a bit. I talked about the 0.25% and maybe on even 0.3%, but really when you're making this design, you really should up it even more. Now, for practical reasons, about the best you can get is 0.4. But again, you try to make the most of what you got. Try and get that EFL as high as possible, and thereby boosting your zero fiber strain margin as well. If you're making the type or the variation with the aluminum, aluminum cladding is preferred to putting the stainless steel tube into an aluminum pipe, because then you have an optical unit that works as an integrated element. When stainless steel tube is inserted in a pipe, it can slide relative to the pipe, it can rotate, and nothing good comes from those things. Let's just say that. When you're making this stainless steel tube in either design, you want inline EFL control. So you want those fibers to all have exactly the same shape and be in phase with one another. So they're all together. 20, 30 years ago, when making loose tubes, you often ended up with what I call loosey-goosey loose tube. So the fibers were in there sinusoidally, but they weren't all in phase with one another. They didn't all have this exact same shape with each other. It was a little bit of a mess. Today's technology, you can do a better job, and you can make sure that each and every fiber has the same amount of excess length relative to the tube. Plus, when you're making the tube, you can add an eddy current testing to verify that the weld, because all of these tubes are made using a welding process, that the weld penetration is perfect and that you have absolutely no holes, voids, bad welds, or anything else. You want 100% perfectly flawless tube, and you can do that as part of your production process. The gel that's used inside these, and by the way, in an aerial cable, you should always use gel. I know dry tubes are a big thing, and some are even trying to use dry tubes with ADSS. That's another conversation for another day. Just let me say, with OPGW, dry tubes would be a especially bad idea. I don't like them for ADSS either. Gel is the way to go. When you're making this type design, the welding process can impart hydrogen to the interior of the tube. And for that reason, you should be using gel that's formulated for this type of tube and that production process. And what it means is that they will add additional hydrogen scavenging to absorb that hydrogen that gets into the tube, which protects the fibers, because fibers don't like hydrogen, and that's always been the case. But also the gel that's used, that's specifically formulated for use in these tubes, has a higher temperature performance. And that's a good thing for OPGW because it can get hit by lightning, which heats up the cable, or it could carry fault current, which again heats up the cable. So you want that increased temperature performance. And you can tell if the gel that's inside the tube in this design type is formulated specifically for use in stainless steel loose tubes or not, because it will have a slight color to it. Whereas the standard gel is perfectly clear. So you should be looking for that color, and you should require that the gel be formulated specifically for use in stainless steel loose tubes. What we recommend is, we talked about using bundling threads and ring or ring markings. But when it comes to making the best of this version of the cable, we think you should use both. It's a little bit belt and suspenders, but when splicing techs are working with the bundling threads. If they're not careful, they can lose track of that bundling thread. And if that happens, they basically got to start over. So the ring markings provide a good backup in case you lose track of the bundling thread. So we like to use both, a little bit of belt and suspenders, but a good practice nonetheless. So next up, aluminum pipe type design. Again, it's loose tube, but as we talked about, there are differences in loose tube. And in this case, the zero fiber strain margin is better, 50 to 60% rated breaking strength, but that's about the best you can do because of the geometry that you have to work with on the inside of that aluminum pipe. But it's good. It means if you can get it to 60, you're at least covering the NESC 250B rules, the traditional limit of 60% rated breaking strength without any fiber strain. That's great. It enhances long-term reliability. I mentioned that splice techs often don't like working with the stainless steel tube, so often they prefer this design type because of the plastic buffer tubes. Another advantage of this design type is that this aluminum pipe gives you excellent electrical properties. So if you're trying to get high fault current, this may be the design to go with because of that. But the disadvantages are, even though the zero fiber strain margin is better, it's still lower than what you can achieve with the last design type, the stranded stainless steel tube that we'll talk about in a moment. I again argue that the stainless steel tubes provide better protection for the fibers than the plastic. The aluminum pipe is relatively inflexible and susceptible to being deformed or crushed, and that's important during stringing, so that's a big disadvantage. As a consequence of that, this design type nearly always requires an anti-rotation device during stringing. And you have to be more careful about the blocks that you use, and pulling restrictions come into play as well. There are some environments too. One of them is here in Texas, where the aluminum pipe can actually be corroded away, and that will expose the interior, and then bad things happen. And this design tends to be expensive because you have more manufacturing steps. You have to put the fibers in a tube, you have to strand them around, you have to then put them in a pipe, and then you have the final stranding process. So that adds cost, all else being equal. Best practice, a big thing that comes up, well, again, the outer wires, you want that conservative lay length and good fit. But then within the tube, what plastic do you use for these buffer tubes? Well, NCAP believes, and I agree, PBD is the best plastic to use. PBD is durable, abrasion resistant, it gives you good crush resistance, and it's stable over the entire temperature range that your OPGW might be experiencing. So that's very important. The tubes then be stranded using reverse oscillating lay. That's very common for ADSS and duct cables. So that's where you strand the tubes in one direction and then you reverse and go in the other direction. That helps separate the tubes when you're doing splice prep. So another reason splice techs will like this design concept. We think it's good to have both a water absorbing material and a thermal barrier. The thermal barrier is kind of obvious because, again, OPGW can get hot when it's hit by lightning or when it's carrying fault current. And the thermal barrier helps protect those plastic buffer tubes. It protects your optical core, as we say. The water absorbing medium, that one's a little bit more subtle. In the field, if a tube is breached, it could be by corrosion that I mentioned before, or possibly what's at least as common, maybe more common, is gunshot damage. A weld failure could be an issue too, but you know, you'll see that we say that it's better to use an extruded aluminum pipe versus welding it for that very reason. You don't have a weld seam to worry about. But back to the water barrier. if a tube is breached, initially the water absorbing material is going to absorb that, but its performance is going to degrade over time. So after maybe, I don't know, 100 cycles or something, it's not going to be as effective at absorbing the water. The water could go to migrate to mid-span and then freeze, and weather like today in Texas and freeze, and the ice expands when it freezes, which could basically end up crushing the fibers. But probably, or the water could migrate through the plastic material and directly affect the fibers. So the problem is eventually you're going to have optical failure, but it should degrade over time. So initially it'll provide some protection and you'll start to see attenuation increase slowly. And eventually that should flag you to go check out what's going on. And then you can make a planned replacement, as opposed to if you don't have a water absorbing material inside the tube, the water could get in, flow to mid-span, freeze, and you'll have immediate failure right away. So it buys you time, as opposed to a crisis at dark 30, on January 2nd kind of thing. Everybody has a bad day when it's a crisis. The water barrier can help you see a problem and head it off in time. And next up is the fully stranded design. Advantages of this design type: it gives you the highest zero fiber strain margin, so you can get 80%, which means not only can you meet the traditional 250B limits with no strain on your fiber, you can even add in the concurrent wind and ice and extreme ice conditions and have no fiber strain. So that's great for long-term reliability. Again, I like stainless steel tubes. It looks and handles much more like a conventional cable, so it's very flexible specifically and crush resistant. And because of that, you generally do not have to use an anti-rotation device during stringing. Some manufacturers will require it, but some won't. At least you have the possibility. And in general, you can go longer pulls through more angles, and that can reduce splice points. So those are all good things. But the disadvantages, it's not as mechanically and electrically efficient. So when you make this cable, you end up with these interstices, and interstices is a fancy word for wasted space. It's just a reality of this cable design. And you're back to your splice techs who might be grumbling about the splice prep. Best practices on all of these: you've seen conservative wire lay length and preform, and with good fit. In this design, like with the center tube designs, you want the inline EFL control and the eddy current testing. You want the special gel, and you want the color-coded bundling threads plus the ring marking to facilitate your splicing prep. In addition, you want to make sure that the stainless steel tubes are a little bit smaller than the wires around them. So this isn't just a drawing error. This is actually an important detail. You want this to create kind of a bridge effect so that any crushing force on the cable, the entire cable is giving way before the tube sees any of that force. As a practical matter, this also helps during stranding to make sure that the tube is not pre-damaged when you're applying the outer wires over the optical core in the center of the cable. So design parameters. So for OPGW, the three most important design parameters are the fiber count, an overall diameter requirement, and how much fault current capacity you want. Lightning performance you may be wondering about, and we will talk about that in a minute. The problem is that these work against each other. So fiber counts over the course of my career have gone up. At the beginning, a 12 fiber cable was a smoking hot fiber count, but today the most common is still 48, but we see a lot of 96, 144, and even some 288. So fiber count drives up your diameter, all else being equal. But the structural engineers don't like that. They want cables to be small so that they put less load on the structure. So these two right off the bat work against each other, plus your fault current capacity works against you as well, because the higher the fault current capacity, the more metal you have to have in order to um, effectively dissipate that energy, whether it's a lightning strike or the fault current itself. You have to have more metals. That drives up cable diameter, but of course, the structural guys, they want diameter to be down. So these interplay with one another, and you end up with trade-offs again. The fiber count is limited within a tube, as I talked about before. For any given tube size, there's a maximum number of fibers that you can put in it and still keep that sinusoidal shape that you want to where it should be. Tube size then relates to your cable diameter, right? The bigger tube means that the wires have to be bigger around it. And so that tends to drive up cable diameter. Talked about that. The tube size itself for an aluminum pipe type, the space inside the pipe is your limiting factor. For a stranded stainless steel loose tube design, it's what the wires that are around it. And for the center stainless steel type, how big of a stainless steel loose tube can you produce? There are some practical limitations there. In general, you would like the diameter to be small, as I keep talking about, but as I've already said, that does limit your fiber count and your maximum fault current capacity. Just to kind of give you some orientation, the most common sizes that we see are 0.465 inches, so just a little under half an inch, up to 646 inches. This is the larger size. So around 12 millimeters to 16.4 is the most common, but we do have some designs that are smaller. Actually, we have some that are a little bit smaller than this. And well, this is supposed to be a typical range. There are some that are larger than this. Now, the reason that you get concerned about overall cable diameter, because you could say, well, why should I be concerned about that, is that the larger the diameter, the more structural loading you're going to experience from ice and wind loads. The larger the diameter, that means there has to be more material there, so that's going to increase the cost of the cable. Plus, the larger the diameter is, it's going to, all else being equal, shorten the reel lengths that you can make, so that that's either going to be a consequence of limitations on the stranding equipment, or how much cable you can fit on a reel of a given size. So it's going to tend to shorten the reel lengths. That's going to mean more setups and the splices. And so both of these factors are basically going to drive up your installation cost. And splice points require more material too. So it's going to drive up your overall project cost, both materials and labor. And as diameters go up, hardware itself gets more expensive too. So basically, as diameter goes up, total system cost goes up as well. Now, let's talk about two of the specific requirements electrically, which are the fault current and lightning performance. First of all, fault current, the required rating should be set by the utility. And then it's the cable designer's job then to meet that. But you, as on the utility side, need to be aware of how that's done. You should have basic familiarity with that. So on the utility side, the fault current is just the expected fault current square times the duration in seconds. A current is generally expressed as kiloamps. do you use single phase or do you use a three-phase fault condition? Well, that's a function of your design philosophy, which is how much risk is acceptable to you. A three-phase fault on a transmission line is pretty rare, but they do happen. So, but you can decide to make an economic trade-off that using the lower current of a single phase fault makes more sense long term, because faults in general are rare. Three-phase faults are very rare. So I can make a case that this is economically more prudent than it is to use the three-phase. And keep in mind that that current is squared, right? So that makes it, if I use 10 kiloamps, I get 100. If I use 20, I get 400. So the square comes into play there. The duration is your clearing time. A single contingency would typically be 4 to 6 cycles. But all relay and control systems that I know of have at least one attempt at a reclose. And if the condition that prompted the fault is still there, you'll have another 4 to 6 cycles. The intervening time period is typically just 1 or 2, so you can kind of neglect that. The cable is not going to cool in 1 or 2 cycles. And so you can sum them up and you get 8 to 12 cycles. Again, a little bit more risk, but that's reasonable. What's most conservative is to allow for failure of the primary protection system and that the fault is cleared with backup protection. In the old days, that used to be 30 cycles, but today that might be significantly less. I say here 22, but it might even be lower than that. Depends on what what equipment you're using. So, you know, as to give you an example, so if I used 10 kA for the current, whether it's single phase or three phase, doesn't matter. If that's what I use, I get 100 times. If I did this, and to keep the math simple, I'll use 6, 12, and 30. So with 6, that's a tenth of a second. So that 100 becomes 10 kA squared seconds is how it's expressed. If I used 12, that becomes 20. But if I used 30, it becomes 50. And the higher the number, the more metal is needed, and all those things I talked about on the previous slide. Now, a cable manufacturer has to take this and turn this into a rating. And there's an IEEE methodology for doing that. And I recommend that everybody use that, because that way you can compare manufacturer A with manufacturer B on an apples to apples basis. If somebody is using their own method or some other method, you may not be able to compare it. Then the two most important variables that go into this calculation, which is to confirm that I'm meeting the rating that you set, are the initial cable temperature and the final cable temperature. Now, the initial cable temperature is not the air temperature, right? Because if you go out to your car on a summer day, it might be 80 degrees outside, but then you get in your car and it feels like 100. Well, a cable, being metal, like your car, is going to heat up more in the sun than the air around it. So for that reason, it's been common practice in the United States, at least, and other parts of the world too, to say the cable temperature was 40 degrees C, which is 104 F. And that had been typical because it's a realistic cable temperature on a hot summer day. Now, I'm in Texas. In Texas in the summer, I could make a case that maybe it needs to be more than that. It may need to, we have days when it's 104, that's the air temperature. So I could make it 50. The flip side of that is maybe if you're located in the state of Maine, you might say, well, our summers tend to be a little bit cooler than Texas. So you might want to set on 30. It doesn't matter what you choose. What matters is that everybody uses the same parameters when they're doing this calculation to verify compliance. That's what I'm trying to point I really want to make here. As a matter of fact, I do know that one utility in Maine did choose 30, and I do know utilities that have chosen to use more than 40 for the very reasons that I just described. Now, what final temperature do you use? Well, you can debate about that, but it turns out for the three designs that, in the case of the aluminum pipe design, you get concerned about plastic material. And in all of the designs, the gel can become a factor. You also get concerned about annealing, loss of strength in the aluminum alloy wires. And as a consequence of that, it just happens that about 210 is the safest that you can go. But that needs to be considered as part of the hottest part of the cable. Some people out there will try to say, well, we'll use this temperature, but at the coolest. And that's just risky. And it's basically a way I would characterize it as cheating. So if I use 210 at the hottest part of the cable and somebody else used 210 at the coolest, they've cleverly and secretly given themselves an extra advantage trying to show you that they're meeting your requirement and maybe trying to offer a smaller or a cheaper cable or something like that. So everybody needs to play by the same rules. Now, about this, you may say, well, we have a lot of 3/8 inch EHS or 7 number 8. Can we just say make it like that? And I try to discourage that practice for two reasons. One is that there's no precision to that. So you can't go get your copy of the Southwire overhead conductor manual and look up the fault current rating for 3/8 inch or 7 number 8 or anything else. It's just not there. In fact, there's not good data for AC resistance that you can use, and you can debate what higher temperature limit to use. Because you don't have optics or AY wire to worry about in these traditional cables. But nevertheless, if you make some assumptions about this, you can get values in the range of 10 to 16 for 3/8 and 27 to 39 for 7 number 8 as an example. It depends on the assumptions that you use. And I submit to you that in today's power grid, we are trying to get a lot more power through our grid than we did 100 years ago. And these cables were adopted around 100 years ago. So things have changed, and it's unfortunate, but you need to sweat this detail and go get the data. What are your fault currents? What durations are you using? And come up with a rating that works for your grid in today's environment. Okay, last up is lightning performance, and I'm sorry, I just realized on over time. I'll try to wrap this up in about 2 minutes. So it's NCAB's belief that if you've designed well for fault current, then you're going to get good lightning performance too. There are no agreed upon guidelines for lightning design, right? I can't, if you say I am in such and such a state, say the state of Florida, I can't say, well, your lightning design criteria needs to be ABC. ABC really should be specified in terms of coulombs. I can say that, but I can't tell you what it should be. You can go Google and you can find flash density maps, but flash density isn't what kills cables. What kills cables is amp seconds, which is a coulomb. And knowing that there are X number of strikes per square mile per year doesn't tell you how strong the strikes were or what their duration was, which is what goes into coulombs. So you can approach this basically with a method that's about half science and about half just plain guessing. So, but you can offer some general observations, and I'll offer these. First, size does matter. So all else being equal, a larger wire is less likely to be burned through than a smaller one. So that means a 3 millimeter wire will do better than a 2 millimeter wire, but a 4 beats a 3 and a 5 beats a 4. So where do you stop? And remember the trade-offs about cable diameter that we talked about before. Nevertheless, some utilities will adopt a minimum wire size, but the most common is 2.9 to 3 millimeters, and these are just totally picked out of thin air. They're not based on any data. Some utilities um, have used traditional cables such as 7 number 8, which has a diameter 3.26, and they say we didn't have any lightning problems with our 7 number 8 cables, so we'll just make that the minimum outer wire size. And that I can respect that thinking, but just keep in mind the trade-offs involved that we've talked about. So size matters, material matters. ACS is better than aluminum alloy wire, but galvanized steel, like 3/8 inch, would be better still because literally there's more steel there. Um, However, galvanized wire isn't used in OPGW because the electrical properties are so bad. As a consequence of this material matter concept, though, some utilities do require an all ACS outer wire, but outer layer rather, but that does make the cable, all else being equal, larger and heavier and cost more. So you just have to consider that trade-off. Wire count is a factor too. So X amount of energy, so a coulomb, so X coulombs will burn Y number of wires. If a cable has 12 on the outside, Y out of 12 is better than if a cable had 8, say. So this would be like a center tube type design. This would be more like a aluminum pipe or a stranded stainless steel loose tube design. There's also a correlation with wire count and overall diameter. So if as a cable diameter gets bigger, a smaller wire actually performs better than it does on a smaller cable, and that's possibly because the arc area has been increased. And another thing to take in consideration is that low footing resistance does correlate with lower incidence of damage. And this has to do with strikes being more likely to hit at or near a structure where the cable is protected in one sense by the tower itself, but also the hardware. So the dead ends or the suspension clamps give them a little bit of protection, and you're increasing the probability of not having damage is what's going on here. What about the design type itself? Again, this is about half science and about half good guessing, but not really guessing. It's from my observation over my career. So the center tube designs are fine; they do good, but the aluminum pipe type designs tend to do a little bit better, and then the stranded designs seem to do best of all, roughly speaking. Okay. Last, I'll close that we do on our website offer our advanced cable engineering system that can help you with your cable selection. You basically enter some data and it'll walk you through a process to help you pick the optimal cable for your project needs. We do, it'll generate a specification for you, including the hardware that you need and give you cost estimates, and you can just have fun with it. And that concludes the presentation. So now let's take questions. And I apologize for going so long. So what questions do we have? Let's see, questions can be submitted through chat. Okay. Okay, or raise your hand and we might be able to allow you to speak. Let's see, I have a question. Do you have a chart breaking down the maximum turn radius for the different OPGW types? Line angles, I mean. Yeah, we have a guideline um, that talks about how you formulate, how you pick splice points, and that's one factor, is how many angles that you can go through. So what you could do for that is uh, drop me an email or drop an email to support@incabamerica.com and we could send you that document. But that is specific to InCab, so my competitors would not, I don't believe, accept our recommendation. Certainly, they wouldn't like to, but we have that. So, any other questions? Okay. That means I take it I either did a really good job or I did a really lousy job. I guess I'll have to hope that I did a really good job. So let me then go ahead and talk about the continuing education credits. Oh, I see a hand raised, so I'll come back to that in just a minute. For maybe those of you that want to go ahead and check out, since I am over, what you do is you'll get a follow-up email, and in that email, there's a couple things. One is a link to a test. You have to take a 10-question test. It's pretty easy, pretty basic. You pass the test with 70% and you get your continuing credit hours. The second thing that's in that email is a link to give us feedback. So please do give me feedback. What I did good, what I did bad, anything you want to tell me. And then the third thing that's there is a link to a recording of this so that you can go and enjoy it again, share it with your friends and families, family members, your work colleagues, even better, share it with your work colleagues. So those three links will be in there. And now Jordan Overby has a question. So let's see if I can make this work. So Jordan, I think I've allowed your microphone. You have to unmute yourself and then you can ask your question. So Jordan, you're welcome to ask your question. Oh, or you typed it. Okay, here. Can you go over some of the requirements for rollers and spans you recommend for OPGW installation? I'd prefer not to do that today because that depends on the design, number one. Number two, I have a separate webinar about installation where I talk about that in detail. That's not a 30-second question answer. That's like a 20-minute answer, and I don't want to take everybody's time up. But basically, let me give you some guidance here. Every cable supplier is going to have installation guidelines. So you need to ask for those. These days, they are also expected to comply with both the IEEE 1138 and the IEEE 524 standards. And in those standards, there are some guidelines on what shivs, or rollers, blocks, whatever you want to call them, what to use. As a general rule, it's 40 times the cable diameter. 40 times the cable diameter as a general rule. But if you get the manufacturer's guidelines, they may tell you that, well, in this condition or that condition, you can use something a little bit smaller, uh, which might be more convenient depending upon what your crews or your contractor have on hand. But again, so the two standards are in the IEEE, the 1138 standard, in particular the 2021 edition of that, does give some guidelines, basic guidelines for stringing blocks to use. And in the IEEE 524, there's also guidance on what you could do. But the basic rule of thumb is 40 times cable diameter. And some suppliers will basically say 40 times diameter, whatever the real length is. And then I see a question. My company is blocking the links to the test and opinion sites. How can we get the recorded webinar? Well, I would recommend that you march to the president or CEO of the company and say, I want the links to NCAB enabled now. So that would be my first recommendation. My backup recommendation would be to forward it to yourself at your personal email and then get it from there. And I can't do anything better than that, I don't think. The lovely and gracious Alexis has been my assistant on this webinar. Alexis, you got any ideas about that?
We'll try to send a different link, a shorter link maybe, in the email. Just kind of wait for the email that comes afterwards, and we'll have more information ready for you.
Yeah. Okay. Good. The other, I also saw that you posted the if you go to our website, which hopefully your company doesn't block, but ncabamerica.com and click on the Learning Hub, you'll find the recording of this webinar. And in fact, you can find a plethora of other webinars that we've given, recordings of those too. So you can go binge watch fiber optic cable topics all day at our website. Hope that helps. All right, any other questions? Okay. I appreciate everybody's time and attention. Again, I apologize for going on too long. Reach out to me if you have other follow-on questions. I don't feel like I satisfactorily answered the questions about stringing blocks, but you can look for future webinars, and please feel free to reach out to us, and I'll follow up with and help you with whatever situation you're finding yourself in. Again, thanks for your time and attention today. And oh, let's see, we have somebody else with a last minute question. Let's see, I see Jamie, I think I've enabled your mic, so you can ask your question, or you can type it in the chat. You'll have to unmute yourself. I can't do that. So Jamie, did okay. Oh. So Jamie, are you should be able to talk now, I think.